Hi, hello, namaste. In this session, we'll be seeing the Maxwell's equations for static fields. So, till now, we have almost come across the electrostatics and magnetostatics, and we have seen various different equations. So, in this session, I just wanted to rebrush those equations, and I just wanted to say that these are the fundamental four equations that Maxwell's gave out, which govern all the wireless channels that we are studying today. Some cases, even the coaxial cable, the wave equations, which we'll be seeing in the further classes, all those electromagnetic principles are based upon these four equations. So let's see the equations. The first equation, here we have the leftmost part in the point form, or we call it as a differential form, and the rightmost form are the integral form. Okay, so the first equation corresponds to the Gauss law, where uh, the point form gives me just the differential form, that is I can solve through differentiation. So it is nothing but del dot d equal to rho e, and the right side is closed surface integral of d dot ds is equal to the volume integral of dv, the volume charge integral. Basically it is a volume integral of the charge that is present in the volume. So to understand this expression, what this expression states, so del dot d is equal to rho v, means to say what, if I have a volume, let us take a volume, and there is some amount of flux that is getting diverged out, or it might be coming in also. It depends on the type of charge. It might be diverging out, or it might be coming in. So if I want to know, if I know what is the amount of charges that is getting diverged out, I mean the field lines that is getting diverged out or converged in, then I can know the amount of charge that is present within that particular volume. Remember? So that's what this equation said. The same thing is being said here. If I take a closed surface, so if I say a surface is closed, then within that surface I can create some small amount of volume, right? There will be a volume that will be present if I say the surface is closed. So that's what this equation says. The surface is equal to the volume, and what are the amount of charges that is present in that volume will be equal to the amount of flux that is coming out of that surface. Fine. What is second expression? Second expression deals with the magnetostatics part, which we have seen very recently, where in magnetostatics we don't have monopoles, magnetic monopoles to be precise. Like my electric charge, I can have two different types of charges, plus q charge and a minus q charge. They both are two different charges. Whereas in magnetostatics, I only have a magnet wherein one part of the magnet will be the north pole, the other part will be the south pole. So I can't differentiate. Even I split upon this particular magnets, I'll be creating again two new magnets which has a north south. So I can't have two different individual charge like thing in my magnetostatics. So with respect to that, this equation states divergence del dot b, divergence of a magnetic field, a magnetic flux density is 0. Okay, divergence of magnetic flux density is 0. That means if I have a charge going out, it is not going out, it is actually continuous. It comes and it joins again to the south pole, and internally there is a flow. So it is a closed path. Okay, that's what this equation states. Or in other sense, if I have a closed surface, then the amount of flux that is emitting out will be equal to 0, because if I say this is a closed surface that I have taken up, what are the flux that is leaving out here will also be entering here within the conductor, or within the magnet. So whatever exits is getting entered, so the both things gets cancelled off, and hence it is 0. That's what our second equation states. And the third equation is del cross E, or the curl of electric field intensity is 0. So it is a conservative nature of electrostatic field. So to mean the other thing, let us see this also. The integral, closed line integral of E dot dl equal to 0. So what this equation states basically, to be keeping it simple, what is curl? Curl is basically, it is used to find the rotational field across any given point in space. Okay, so if I say electrostatic field are not closed path. So electrostatic field starts at one point and it ends at other point, right? So I don't have a closed path. It has a beginning and it has an ending for my electrostatic charges. So if the beginning is equal to ending, then I can call it as a closed loop, just like magnetostatics, right? Whereas in my electrostatics, I don't have that beginning and ending to be same. Hence, the curl of my electric field will be equal to 0. So there is no curl or rotational effect of my electric field, or in other sense, if I have an electric field, a uniform electric field, and I started from point A, I moved the charge from point A to this plane. I moved in this path, and again I reached point A itself at the end. So the work done by me will be equal to 0, because if I say the initial point and the final point are same after integration, so this is nothing but initial minus final, both are initial, ei minus ei after solving, so it is 0. So you can't expect the work to be done when you do in a loop or in a closed path. That's what this equation states. And finally, the equation of magnetism, where del cross H equal to J, our curl of H equal to J, where J is a current density, or in other sense, the line integral, the closed line integral of H dot dl equal to surface integral of J dot ds. So what was this equation stating us, or what this means? Basically, if I have a magnetic field, okay, if I have a magnetic field around a closed path, then I can know what is the current, okay, what is the current that is enclosed within that path. So it is going to give me the density of current that is flowing within or in that space where the closed line is being enclosed. If del cross H is 0, then there is no current at all. So since del cross H is equal to J, the curl of H equal to J, I can get the current density that is flowing within that particular surface. So that's where we have related my H and J, or magnetic field intensity, or in other sense, if I have what this equation, the integral equation states is, if I have a closed line wherein I am calculating the magnetic field intensity over this length, okay, I have a closed path, I am calculating the magnetic field intensity, then I'll be getting what is the amount of current that is flowing through this surface. Okay, since I have a closed path, the closed path can make a surface, right? So if I have that surface, I can calculate what is the amount of current that is within that surface, which is flowing out or flowing in, or it depends. So that's what this equation states. So these are the main four fundamental equations of Maxwell's, which we have our concept on, and these are the main four equations on which all the electromagnetic principles are based upon. So if you are good with this, or if you have understood this, you have intuitively understood this, then the concepts will be very, very, very easy to you to imply, or to understand, or to even to get some applications out of it. So hope these concepts are clear and understood. Thank you.